Thank you. I'd like to start by thanking the organizer for giving me the opportunity to talk in this wonderful conference. Thank you. And the problem that I'm going to talk about is my thesis problem from last year. So I'm just going to present the results that I got. So let me first write it down. And then we're going to discuss. So the problem is to classify the families of special Lagrangian fourfolds in C4. So by fourfolds, I just mean 4-dimensional submanifolds, whose fundamental cubic and I'm going to explain what it's meant by a fundamental cubic, but special Lagrangian, has non-trivial stabilizer in SO4 at the generic point. And I'm also going to discuss the motivation for considering this problem. So this problem generalizes the results of Robert Bryan, who completely classified the special Lagrangian threefolds in C3, whose fundamental cubic have non-trivial stabilizer. So generalizes, extends results. Robert Bryan. So he completely solved the problem in dimension 3. Okay, so what would be the motivation to consider such a problem? So first of all, special Lagrangian geometry is important nowadays because of the relation with mirror symmetry. So people would like to know what are the special Lagrangian in Calabi-Yau. But special Lagrangian are not well understood, not even in the flat space, Cm, except for dimension m equals 2. So for m equals 2, the special Lagrangian is just a holomorphic curve, with curves with respect to an alternative complex structure. But for m equals 3, there is not a classification of special Lagrangian or anything like that. But lots of people constructed lots of examples of a special Lagrangian. And the methods they used various methods. But if you remember, the special Lagrangian satisfy a PDE, which is second order and fully nonlinear. So to solve that PDE is very hard unless you impose some symmetries on the special Lagrangian. So people like starting with Harvey and Lawson and continuing with Mark Haskin, Dominus Joyce, and many others, constructed special Lagrangian with symmetries. So you have just a group action on C3, and the special Lagrangian are just symmetric under that group. In this problem that we're considering, we have a different type of symmetry. So we're putting a symmetry on the second fundamental form. This is actually what the fundamental cubic is. The second fundamental form of a special Lagrangian can be interpreted as a harmonic cubic in 4 variables if we're considering the fourfolds, or in m variables if we're considering the special Lagrangian in Cm. And I'm going to explain how we get this fundamental cubic. So, so in here, we're considering symmetries on the way the special Lagrangian sits in Cm. So the second fundamental form. Because the ambient space is flat, the second fundamental form of the special Lagrangian is the lowest order invariant. So that's why we're looking at the lowest order invariant. But of course, well, people might generalize and look at higher order invariants. Okay, so I would like to present also an analogy with the classical theory of surfaces, what it means to look at special Lagrangian whose second fundamental form has a non-trivial stabilizer. This is analog to looking at special Lagrangian whose points are umbilical. And why is that? Because, for example, if you have a hypersurface in Rn plus 1, and you consider the second fundamental form of this hypersurface, so you can just write it in an orthonormal coframe. So K1 omega 1 squared, K2 omega n squared. So these are K1, K2, Kn are the principal curvature. We notice that SON acts on the second fundamental form. And the stabilizer of the second fundamental form is non-trivial, always. And its maximum exactly at the umbilical points. For example, if K1 equals K2 equals Kn, we get the maximum, which is SON. Now for special Lagrangian in Cn, so special Lagrangian manifolds, I'm going to just denote special Lagrangian by SL from now on. So we notice, I mean, it can be proved that for a generic special Lagrangian, the stabilizer of the second fundamental form at the generic point is trivial. Okay? So we are considering exactly the case when this stabilizer is non-trivial, meaning we're looking at special Lagrangian whose whose points are all umbilical, the generic point. So this would be the motivation for this problem. Okay, so let me just, so from now on I'm just going to consider, so I'm going to leave the problem here. I'm just going to consider our manifold to be C4. But let me remind you the definition of a special Lagrangian in Cm. So I'm going to say let M equal Cm. So Cm is a Calabi-Yau, and the Calabi-Yau structure on Cm is given by the Calabi-Yau metric. So let's just choose holomorphic coordinates Z1, Z2, Zm. So the flat metric is just given by dz1 bar plus dzm bar. Then we have the symplectic form, I over 2 dz1 bar plus dzm bar. And then we have the holomorphic form, which is just dz1, which dz2, which dzm. Holomorphic volume form. So with this metric symplectic form and holomorphic volume form, Cm is a Calabi-Yau. Now, I'm just going to define what is a special Lagrangian in Cm, but it can be generalized for any Calabi-Yau. So as a real m-dimensional oriented submanifold L in Cm is called special Lagrangian. If it is calibrated by the real part of the holomorphic volume form. So this is a definition. These are exactly the special Lagrangian, the submanifolds, m-dimensional submanifolds calibrated by this form. But a more useful and equivalent definition, characterization would be, is the same with the fact that the symplectic form vanishes on L and the imaginary part of the holomorphic volume form vanishes on L. So this is what the special Lagrangian are. Okay. So now let me just quickly review the results that Robert Bryan got in dimension 3 so that you see the parallel, some of the cases appear also in dimension 4. So just quickly, results Bryan 4, n equals 3. Okay. So let L in C3 be a special Lagrangian submanifold with fundamental cubic C. I didn't explain what is the fundamental cubic, but I'm going to explain in a minute. And let G be the stabilizer, let's say SO3 stabilizer, because SO3 acts on the space of harmonic cubics at a generic point. So G at a generic point. So the question is, what are the special Lagrangians that have this G non-trivial? Okay, so the cases are, so when G can be maximum SO3, then in this case you just get the 3 planes. So the special Lagrangian are 3 planes. And of course the fundamental cubic is just 0, I mean on the orbit of 0. Then the stabilizer of the fundamental cubic could be SO2. And in this case, he gets the Harvey-Lawson examples. I'm going to write them explicitly because they also appear in dimension 4. Harvey-Lawson examples. Invariant under SO3. So these are actually the only special Lagrangian which are invariant under this group SO3. And the Harvey and Lawson wrote explicitly how they look like. So note that this is the symmetry of the manifold, while this is the symmetry of the second fundamental group. So this is the stabilizer of the fundamental cubic. Then the stabilizer can be the symmetric group on 3 elements. And in this case, you just get the Auster or Auster 3 submanifolds. I don't know how to pronounce Auster. Auster, yeah. So just a class of minimal submanifolds. And they are classified in dimension 3, what they are. But I'm not going to say here. Then if the symmetry is Z3, then he gets the asymptotically conical. So the special Lagrangian is just an open set of asymptotical conical special Lagrangian. Special Lagrangian threefolds. It's within dimension 3. And then the least symmetry, Z2. In this case, he gets something called Lawler-Harvey-Joyce example. So these are basically, if you have a quadratic surface which sits in a Lagrangian plane, P, Lagrangian 3 plane, they are exactly the special Lagrangian extension of this quadratic surface. So these are these examples. Okay, and then there is another case here, G equals A4. So also this group stabilizes a fundamental cubic, I mean a harmonic cubic, but in this case no special Lagrangian. So this is how the classification looks in dimension 3. Okay, so for dimension 4, the situation is a bit more complicated because there are more groups of SO4. Oh, I didn't want to erase the problem, but anyway. And I will start by defining what is the fundamental cubic of a special Lagrangian and the structure equations of a special Lagrangian submanifold. So first of all, structure equations of a special Lagrangian in C. And I'm going to also define, I'm going to show how the second fundamental form can be interpreted as a harmonic cubic. So in our case, I'm going to just write the structure equation in general for Cm, and then in my particular case, M will be 4. So this is with the standard Calabi-Yau structure, the metric, the symplectic form, and the holomorphic volume form. Now, I'm going to consider the bundle of Cm-valued Calabi-Yau coframes. So P. So let P from P into M be the bundle of Cm-valued Calabi-Yau coframes. So how does an element in P look like on a fiber? This is the fiber Px. Okay. So an element U in Px is just a complex linear isomorphism between the tangent space of M at X and Cm. Right, because M is a complex manifold. So this is the linear, complex linear isomorphism. So remember that on Cm I had the symplectic form and the holomorphic volume form, such that and this forms just pull back to P on the bundle. So we have U star omega 0, omega x, and U star of big omega 0, big omega x. Right. So now omega and big omega are on the bundle, forms on the bundle. Okay, with this, and I'm going to erase the problem. So this coframe bundle, P, from P into M, is a principal right SUM bundle. So the group that preserves this metric, the holomorphic volume form, and the symplectic form is exactly SUM. So pi is just a principal right SUM bundle, and the action, the right action, is just given by, so an element from SUM acts on a coframe, and it's just A inverse U. So this is usual multiplication, because A goes from Cm to Cm and U from the tangent space of M to Cm. So you can compose them. So this is the action. On this bundle, principal SUM bundle, we have the canonical one form, Xi. So let Xi be the canonical one form on P. Okay. How is it defined? It's exactly as you would expect. So we have d pi at U is going to be from the tangent space of P at the coframe U into Txm. And then I can compose with U that goes from Txm into Cm. Right? So this is going to be defined just U composed with d pi U from TUP into Cm. Right? So this, the canonical one form, takes values in Cm. Okay. And I'm going to just denote the components by Xi, I from 1 to M. So these are the components of the canonical form. Okay. So now we have Cartan's first equation, which will give us the connection form. So Cartan first structure equation. We'll just take the differential dCi equals, it's going to be minus psi ij wedge xij. And this is the connection form. And of course takes value in the Lie algebra of SUM. So psi ij takes values in SUM. So it's a skew-symmetric matrix with trace 0. Skew-Hermitian. And sum of psi I equals 0. Right, so this is the connection form. And then because our space is flat, Cm, we have the second, Cartan's second structure equation, which tells us that the derivative, so d psi, so Cartan's second structure equation is just d psi equals minus psi wedge psi. There is no curvature term plus r because we're in the flat space. Of course, this should be written as, well, I don't put the coefficients, but I write it as a matrix psi ij. Okay, so the canonical one form, I mean the components of the canonical one form, psi I, and the connection form just form a basis for the one forms on the bundle P, for the space of one forms on the bundle. Okay, now, so these are just Cartan structure equations. And now, because we want to study special Lagrangians, we'd like to adapt frames, not to consider any Calabi-Yau coframe. And we're going to consider the bundle of adapted coframes. So this is P, the Calabi-Yau coframes. And now we're considering a special Lagrangian L. And we know that the tangent space of the special Lagrangian is real, always. So we'd like to adapt these frames. And we're going to consider, so let L in Cm be a special Lagrangian M-fold. Okay. And now let's take X on the special Lagrangian. Now, a coframe U in the fiber is going to be called L-adapted. So a Calabi-Yau coframe U in the fiber at X is called L-adapted if it takes the tangent space at L, the XL, which is of course in the XM. This is M equals Cm into a real one, into Rm. If U of TXL equals Rm, right? And as a subspace of Cm, and U preserves orientations. Special Lagrangian are oriented. And now we consider just PL, the sub-bundle. We collect all these L-adapted coframes, and this is going to form a principal right SOM bundle, not SOM anymore, because it takes a tangent space to the special Lagrangian to Rm. So PL in P is going to be the sub-bundle of L-adapted frames, coframes. And PL is the principal right SOM bundle. Over L. Okay. So this is the setup. And now let's see what the structure equation become when restricted to this bundle, to this L-adapted coframe bundle. So for this, we're gonna we're gonna break up the canonical one form into real and imaginary part. So we're gonna write psi I equals omega I plus root of minus 1 eta I. So I just write this not to be confused, the I here with the I here. And the canonical, the connection form also, I'm gonna write it as alpha ij plus I beta ij. Okay, and now I'm going to see what Cartan's first structure equation becomes when split into real and imaginary part. So if you just plug in psi I and psi ij there, and you collect the real and imaginary part, you're going to get the following. So, so you just get d omega I. So you're going to get an equation for the real part of the canonical form, and then for the imaginary part. So d omega I is going to be minus alpha ij wedge omega j plus beta ij wedge eta j. And d eta j is going to be minus beta ij wedge omega j minus alpha j with beta j. So I'm writing this structure equation because I need them to define the fundamental cubic, and then this structure equation I'm going to use all the time. Okay, now since the connection form psi has values in SUM, is SUM valued, it means that alpha, the real part of psi, is going to be antisymmetric, and then beta is going to be symmetric with trace 0, right? Because psi was with trace 0. It means that alpha ij is negative alpha ji, and beta ij equals beta ji, and sum of beta ii equals 0. Right. So alpha is the real part of the connection form, beta is the imaginary part. Okay, and now what does the second equation, structure equation of Cartan becomes, which I wrote it, well, probably I erased it, but it was d psi equals minus psi which psi. So when you break it into real and imaginary part, it becomes, and I'm not going to write the indices anymore, so you understand it's d alpha ij equals minus alpha ik, which alpha kj plus beta ik, which beta kj. So it's just, maybe I'll just write it so I don't get confused. Kj, ik, kj. Right. And then the imaginary part, the beta ij, is going to be minus beta which alpha minus alpha which beta. Right, so the same convention. I don't write the indices anymore. This is a Gauss type equation. This is Codazzi. And these are going to be exactly the compatibility equation for the existence of the special Lagrangian. So we're going to have, so let me just tell you what this structure equation become when I restrict it to the L-adapted coframe, because this was still on the Calabi-Yau coframe. But now, when restricted on PL, the L-adapted coframe bundle, because a coframe takes a tangent plane to the special Lagrangian to a real one, it means that the canonical one form is just Rn valued. So it means that eta I all restrict to 0 when restricted to this L-adapted coframe bundle. So we have eta I equals 0. Okay, so this is on PL. And then if you look at here, so this one disappears, and so eta I is 0, eta I disappears, and we just have that beta ij wedge omega j is 0 on the bundle, on the sub-bundle. So beta ij wedge eta j is 0, omega j, also on PL. Now, because omega 1, omega 2, omega n are just linearly dependent, right, on that, from Cartan's lemma, we have that beta ij must be a linear combination of these omegas. So beta ij should be some function hij(k), omega k, where hij(k) is symmetrical on the last two indices. This is from Cartan's lemma. But we know also that beta are symmetric on I and j. So that means that h also is symmetric on I and j. So in the end, the function h on the restricted to the, this function h on the subbundle PL are just fully symmetric. So also hij(k) equals hjik, because beta is symmetric. So the hij(k) are fully symmetric functions on PL, right, on the bundle, subbundle of L-adapted coframes. Okay. So now I'm ready to define the second fundamental form. So we know that the second fundamental form is just a quadratic form with values in the normal bundle. And we're going to just choose a framing compatible with adapted to the special Lagrangian, right? So U1, U2, n, it's in the space tangent to the special Lagrangian, and the j's are in the normal bundle. Then, the second fundamental form of the special Lagrangian is just the quadratic form Hij omega j omega k with values in the normal bundle. So actually we notice that all the information of the second fundamental form is encoded in the following cubic. So we can just say the second fundamental form. The information is encoded in Hij omega I omega j omega k. And this is called the fundamental cubic, the special Lagrangian. Call it C. So fundamental cubic of L. Right, so we just need to know the Hij to know the second fundamental form. There is one more thing to show. Actually, this cubic is, well, it has trace 0 with respect to the metric. So it's going to be a harmonic cubic. So let me just write. So, remark, C is traceless with respect to the induced metric on the special Lagrangian. So this can be seen very easy because the trace is just Hiik omega k, which is beta II, but the beta were traceless, so is 0. We can show, it's very easy to show that actually a traceless cubic is the same with a harmonic cubic. So actually the fundamental cubic of a special Lagrangian belong to the space of harmonic cubics on 4 variables. In the case I'm considering n equals 4. If not, it would be r to the n. So let me go back to my case, n equals 4. So the fundamental cubic of a special Lagrangian that I want to study will always be in this space. So this is harmonic cubic. Cubics in cubic polynomials in 4 variables. So just x3, x4. Right? Okay. And there is a Bonnet type theorem that tells you what are the necessary and sufficient conditions for the existence of a special Lagrangian, and it is exactly what you would expect. The Gaussian-Kodazzi equation are the only condition. So Bonnet type theorem just tells you the necessary and sufficient conditions for the existence of a special Lagrangian, let's say m-fold in Cm with a given metric and a given symmetric traceless cubic C as its fundamental form. Are the Gauss-Kodazzi equations. So if the Gauss-Kodazzi equations are satisfied, there is a special Lagrangian in Cm. Okay, so so coming back to the problem that we want to solve, we want to find all the special Lagrangian whose fundamental cubic have a non-trivial stabilizer in SOM. So you can see that SOM acts on this space. So this space of harmonic cubics in 4 variables actually is an irreducible SOM module. And we would like to find those fundamental cubic that have a non-trivial stabilizer. And then to describe the special Lagrangians with that fundamental cubic. So H3 R4 is an SO4 module. Well, irreducible. So of course it's true in general for Rm, but I'm specializing to my case. So in this case, n equals 4 of dimension 16. and SO4 acts just by pullback on this space. So, we'd like first to know what are the possible harmonic cubics that have non-trivial stabilizer under the action of SO4. This is what we'd like to know first, because we don't care about those that have trivial stabilizer. So first of all, the first problem would be find all harmonic cubics C in H3R4. So in 4 variables, x1, x2, that have non-trivial stabilizer G under the action of SO4. So first of all, we find all these harmonic cubics. And then once I know, we have to find if there is any special Lagrangian having that particular harmonic cubic as its fundamental cubic, and also describe it. I mean, if it's, we can describe it. So first of all, well, I'll just say 2 words about how we could find out what are all the harmonic cubics that have non-trivial stabilizer. And then I'm going to talk about what we get, I mean, the classification. So first of all, the maximal torus in SO4 is conjugate to the group. So it's going to be e to the 2 pi I r. I'm going to write it like this, e to the 2 pi I s. So any element in the maximal torus will basically look like that. And now, to be easier, we're going to consider the space of complexified harmonic cubics. So let's, because we're going to recover the real harmonic cubics from them. So how did I call them? HC3. So these are going to be the complexified harmonic cubics in Z1, Z2, Z1 bar, and Z2 bar. Right? So here, delta is just the DZ1, DZ1 bar, as the DZ2, the DZ2 bar. Right? So we want the harmonic cubics. And now, of course, to relate to my real harmonic cubics, my Z1 is going to be just x1 plus ix2, and Z2 x3 plus ix4. Okay. Okay. And now, actually, the maximal torus in SO4 acts on this space of complexified harmonic cubics, and I'm going to show you because it decomposes into weight spaces of multiplicity 1. I don't know if I, kind of. So this is, I don't know, it's out of focus. So this is a space of complexified harmonic cubics, and under the action of the maximal torus, it just decomposes into 8 pairs of opposite weight spaces. And I wrote them. So there should be 16, because if you notice, they are opposite. 3, 0, minus 3, 0, 2, 1, minus 2. So these are just the weights, 3, 0, minus 3, 0. And then I'm going to explain this picture in a minute. But let's see how we recover the harmonic, the real harmonic cubics. So the real harmonic cubics is just the sum of elements from these weight spaces with the coefficients in the opposite weight spaces being complete conjugate. So it should be, for example, if I consider A times an element from this space plus A bar, an element from this space. So you cannot just take any element from this space, B, because you wouldn't get a real harmonic. So this is how you obtain this, and you would like to have a fixed harmonic, real harmonic, because you are looking for fundamental cubics with non-trivial stabilizers. So, what maybe? So there exists a fixed harmonic cubics at, if and only if. So you should find a non-trivial element in the maximal torus that would act trivially on at least one of this pair of spaces, right? So for example, on this and this should act trivially, or on this or this, or on this and this and this and this. So all the combination you could, but it should act at least on one pair. If it doesn't, it means there is no fixed harmonic cubic. Okay, so these possibilities is exactly how we got these weight spaces. So now I'm going to explain this figure, this picture. So this triangle is because I just restricted to a fundamental Weil chamber. So I just mod out by the Weil group of SO4. And this, the possibilities are exactly the 8 lines that are inside this triangle. So for example, 2R should be in Z is one possibility. That means there is a non-trivial element. There is a non-trivial element acting trivially on this and this, on this pair. That's exactly saying that 3R is in Z. So there is this line. Okay, and then, for example, 2R plus S. 2R plus S, so this line. Right, so this line should intersect this little triangle. So I just want to show like one example. So I'm just going to keep that up. So to understand how this non-trivial, I mean how this fixed, how you get this fixed real harmonics. So for example, if we consider 2R plus S in Z, so there is that line here, right? So we have 2R plus S in Z. Then what is the element in the maximal torus that acts trivially on one of these weight spaces? So it's going to be G e to the 2 pi I R e to the 2 pi I S. So acts trivially on, so on what pairs? It's going to be on the pair V of 2, 1, right? And the opposite pair, minus 2, minus 1, with the opposite weight. So a basis here is formed by the harmonic, complexified harmonic cubic Z1 square Z2. And a basis here is Z1 bar squared Z2 bar. Okay? And you can see very easy that this element G, when acts on Z1 square Z2, is just e to the 4 pi I R, right? Because you square it, e to the 2 pi I S Z1 square Z2, right? Because how it acts is just, so the element here, Z1, just goes to e to the 2 pi R Z1, and Z2 goes to e to the pi I S Z2. And then here, this is just e to the 2 pi I 2R plus S, Z1 square Z2, right? But this is in Z. So this is 1. So it just fixes, right? So this element just fixes this complexified harmonic cubic. But I don't want a complexified harmonic cubic. I want a real harmonic cubic. And you can see also that this acts trivially also on the bars, right? And to get a harmonic, real harmonic cubic, as I told you, you just take a combination of this plus a bar, combination of this, right? So the coefficient should be complex conjugate in the two weight spaces which are opposite. And this is exactly twice the real part of A, Z1, Z2. And A is real, right? So this is exactly the real harmonic cubic, which is fixed by this element, right? Okay. So, well, I'm going to, well, just skip the details. But basically, in this space, if you are just on one of these lines, so if you have an element that fixes just, there is a non-trivial element in the maximal torus that acts trivially only on one of these pairs, then the stabilizer is going to be continuous. For example, in this case, 2S plus R is going to be 2 pi I R, and e to the 2 pi, well, S, let's say you can do mod Z, and you can realize that this is continuous. It's not discrete stabilizer, right? So this is going to be rotation by theta, and this is rotation by minus 2 theta. So it's just an SO2. It should contain an SO2. So if you are on these lines, you just get continuous stabilizer. And if you want to get a discrete stabilizer, then you have to be, so you have to find an element that acts trivially on more than one pair of these spaces. So you have to be at the intersection. So I explained to you that I'm just restricting to this triangle because I'm mod out by the Weil chamber of SO4, But actually, if you mod out by the Weyl-chamber SO4, you should be in this big triangle, right, under S equals 1 minus R and R equals S. But you can actually mod out by the Weyl-chamber of O4. And you're just restricting, it should be, for example, this triangle. But as I worked out with this one, just kept it like this. So it doesn't matter. This or this is the same. So there are how many elements? If you want to get a discrete stabilizer, there are exactly 6 non-trivial elements that act trivially on more than one of these pairs. And these are exactly this, and this. So six elements. So we have 2 cases here when we have continuous stabilizer, meaning G is a positive dimensional group of SO4, subgroup of SO4, or discrete symmetry, when it's a discrete. And so we're going to consider those 2 cases. And anyway, so the analysis being done, you just can write all the harmonic cubics that have non-trivial stabilizer. So, and they're basically when G is a continuous subgroup of SO4, then G discrete subgroup of SO4. So here G is the stabilizer of fundamental cubic of a special Lagrangian in C4. Okay, and because I just have 12 minutes left, I'm just going to present the results. So what we get in each case. So for example, if G is a continuous subgroup of SO4, then we're able to write the fundamental cubic with that symmetry. So in this case, for example, if G equals SO4, then the fundamental cubic is on the orbit of the 0 harmonic cubic, and it's nothing here. The special Lagrangian are just the real 4 planes. Now you would wonder how, after we find out what are the harmonic cubics that have a non-trivial stabilizer under the action of SO4, how can you realize if there are any special Lagrangian with that fundamental cubic, and if there is, how you can describe them? So the method, after you write exactly, for example, when G equals SO3, you write the fundamental, the harmonic cubic that have this symmetry. You can see that the SO3 is here, and the next one is fixed. Then you can use the method of, well, you can use the Cartan-Keller theory, basically from the subject of exterior differential systems. You set up a differential idea on the L-adapted coframe bundle, PL, and then you use the Cartan structure equation that I wrote. And then this method tells you if there are any special Lagrangian with that symmetry, I mean with this harmonic cubic as its fundamental cubic. And so basically it's just some Cartan-Keller method. And this method guarantees to tell you if there are any solutions, if there are any special Lagrangian, but it doesn't give you the description, for example, that I wrote here. So this description, you just get them by looking at the structure equation, trying to integrate them, or just looking at foliation by submanifolds and putting them together, and recognizing, for example, all these examples were already written by Harvey and Lawson. So you just recognize that this would be that example. In this case was particularly easy because if you look at the structure equation of the special Lagrangian, so first of all, Cartan-Keller theory tells you that there is a special Lagrangian with a fundamental cubic with this symmetry, SO3. And then if you look at the structure equation, they have an SO4, they are SO4 invariant. And Harvey and Lawson wrote the only examples of special Lagrangian fourfolds that are invariant in C4, that are invariant under SO4, he already wrote them down. And they basically look like, let me just, so you can write them explicitly. So they look like S plus IT U, where U is in the 3 sphere in C4, in R4. And there is a condition on this S plus IT. So the imaginary part to the third equals 0. So this is a special Lagrangian condition. So this is an explicit, these are the Harvey and Lawson examples. And so they are special Lagrangian in C4. Oh, this is C7. Oh, I am in, yeah, equals or constant. Yeah, okay. And the imaginary S plus IT, I think it's to the fourth if I'm in dimension 4.
Yes.
Right, okay. Okay, so this is in C4, S3. Okay, so these are, this just gives you a family of special Lagrangian submanifolds in C4 with symmetry SO4. So these are SO4 invariant, and they are the only examples which are SO4 invariant. And for each C, it gives you, as I said, a family. For C equals 0, you get just the union of 4 Lagrangian planes. So it's singular. But for C greater than 0, I mean, for C not 0, it just gives you a smooth special Lagrangian. Okay. So for this symmetry SO3, we just get an open subset of this. This is how the special Lagrangian looks like. Now, there is another case when G is O2, where O2 is S1, so a circle union G, where G is this element in SO4. So this is a disconnected, of course, subgroup. And the fundamental cubic that has this symmetry just looks like that. So this one, you just, these cubics, you just get them by, well, I erased, but I was doing an example when I wrote exactly what is the harmonic cubic that is stabilized by a certain group. So, and you can write them in complex, Z1, Z2, and then you just, I mean, it's going to be a real part of harmonic cubic in Z1, Z2, Z1 bar, Z2 bar, and then you pick up, I mean, you just write them in real coordinates x1, x2, x3, x4. And in this case, the Cartan-Keller analysis gives you no special Lagrangian with this symmetry. Then there is another O2, which is, so this O2 was rotation by theta and rotation by double theta, but in this case, it's just e to the I theta, this circle. And then also this G is the same. And the fundamental cubic looks like that. Of course, R shouldn't be 3 nu, because if it is, you just recover this case, and the symmetry is larger, it's SO3, it's not O2. And in this case, you get, the analysis tells you that there is a 2-parameter family of special Lagrangian, but I wasn't able to integrate it completely. And basically, I mean, I think it would work if you just use reduction of symmetry and solve an ODE by the method that Dominic Joyce was doing, because actually you could find out what are the, what is the symmetry of the structure equation. So it's basically an SO3. It depends on the parameters. If nu is 0, then it's degenerate. It's an SO2 cross R2. But, well, this, I should do it. I don't know how hard it is, but, I mean, to solve that ODE, first of all, I didn't write it down yet, but you have to solve that ODE on the orbits, and then probably it's going to involve some Jacobi elliptic function. I don't know. So now if G equals SO2 semi-direct product with S3, so the fundamental cubic looks like that. It's on the orbit of this harmonic cubic. And in this case, you get, there are special Lagrangian, and they are just open sets of products, like sigma in C2 is a holomorphic curve with respect to an alternative complex structure. That means sigma is actually a special Lagrangian in C2, because all the special Lagrangian in C2 are holomorphic curves with respect to another complex structure, cross R2. So these are, and then the last case of continuous symmetry is SO2. And in this case, this is how the fundamental cubic looks like. With, you can make S and nu positive by rotation. And in this case, you get the SO3 invariant special Lagrangian 4-folds. So basically, the orbit of this action are 2 spheres. And then you get a manifold in the quotient. And that manifold has an almost complex structure such that the special Lagrangian quotient detection is just a pseudo-holomorphic curve. So it's been described, actually. And it's known what are the SO3 invariant special Lagrangian 4-folds. And in the last 5 minutes, I'm just going to run through what you obtain when the symmetry is discrete, actually. So, and some of the cases are not complete. When the symmetry is very small, the problem gets harder, of course. So, so you have when G is a discrete subgroup. So there would be 2 cases, because the subgroups have SO4 are the cyclic, dihedral, and then you have the polyhedral symmetry, which are basically the tetrahedral, octahedral, and icosahedral symmetry. But in SO4, you have actually two octahedral groups. One acts irreducibly, one irreducibly, and the same, two icosahedral subgroups. And this O+, it means the irreducibly acting, because the reducibly acting actually doesn't stabilize, doesn't preserve any harmonic cubic. So I don't look for special Lagrangian because I'm looking just for special Lagrangian that have non-trivial stabilizer. So for example, if G, the stabilizer is the tetrahedral, so the symmetry of the tetrahedral, the fundamental cubic looks like this. It has two parameters. Of course, again, you have a condition here, because if this is satisfied, you fall into this case. So you have to eliminate it. In this case, you get the Harvey-Lawson example invariant under, this should be R, T3. So again, Harvey and Lawson wrote down this example explicitly, how they look like, and they are the only examples of special Lagrangian in C4 invariant under T3. So, oh, actually, no. In this case, you get, because he wrote a whole family, so the constant can be anything. But in this particular case, I obtain, let me see. So in the case G equals T, the special Lagrangian is just an open subset of the special Lagrangian that looks like this. Z3 equals Z4 equals 0. No, of course not equals 0. And then real part of Z1, Z2, Z3, Z4 equals the fifth root of 2. So this is what we obtain if you want to have this particular symmetry, T. Okay. So, and then when G equals O+, so the irreducible acting octahedral group, you obtain the Harvey and Lawson cones. So these are the cones on flat three-dimensional tori. Again, you can write it in this form, only that here you have 0. So there is a singularity. And they just, so you have the Clifford torus on the 7th sphere, and you consider the cone on it. So this is how this look like, right? Well, they are cones, right? The union of two cones, right? This is T, T1 and T2, and T2 is the minus of T1. Obviously. Okay, so this is, and then in the case when you have icosahedral symmetry, irreducibly acting, there is no special Lagrangian with this symmetry. So these are the polyhedral symmetries. And then to look at the other discrete groups of SO4, if you look at the, let me see, at this picture, you have to consider these elements here, right? So for example, the non-trivial element that stabilizes, that acts trivially on this pair and this pair, meaning it's at the intersection of this and this, it's going to be order 6. So it's easy to find out because R equals 2 over 3. S here is 1/6. So you can write the element of the maximal torus, and you realize it's an element of order 6. So this is going to be order 6, order 5, 4. There are 3 elements of order 3 here and here, right? And then this one is order 2, right? So these are the 6 non-trivial elements in the maximal torus that preserve the text non-trivially. And then we're able to show that if G, the discrete stabilizer of a special Lagrangian, has an element of order 6, then the generical, I mean the fundamental, the cubic that is preserved, harmonic cubic that is preserved that by an element of order 6 looks like this in general. So you can rotate and make it have only 2 parameters here. You have make a rotation in SO4, so you can get rid of some of the parameters. In this case, there are no special Lagrangian. So the Cartan-Keller analysis just tells you there are no special Lagrangian. So now, if G has an element of order 5, so you are, well, in that picture, there are 6 points there, so you just consider them. The general cubic looks like this. Again, you can make it depend only on 2 parameters, no special Lagrangian again. And if it's an element of order 4, and it's not one of the polyhedral groups, again, no other special Lagrangian. Okay. And then the harder part would be if there is an element of order 3 and 2. So the other 2 cases. And in this case, let me just tell you what we did for an element of order 3. There are 2 inequivalent orbits in this case. And these are this and this. Both are elements of order 3. So in this case, it was only one orbit for 6, 5, and 4. But here we have two inequivalent orbits. And the element of the maximal torus that stabilizes